Hey everyone, and welcome to week 3 of our remediation work. And this week we're going to be talking about periodic trends. And so as we talk about periodic trends, we're really talking about what's going on between the nucleus and electrons and how that interaction between the nucleus and electrons can affect some properties, anything from chemical reactivity to some other defined properties of the atom that we've talked about. And so as we kind of make a look at that, so we're going to talk about some kind of overarching patterns and trends that are going on within the nucleus, and then how those patterns and trends and interactions between the nucleus and the electrons come together to affect, things like ionization energy and atomic radius, metallic properties, ionic radius, electronegativity as you move across the period, and how those same changes and interactions between the nucleus and electrons can affect properties as we move down a group. So again, similar properties, but we'll also kind of look at reactivity as well. And so as we kind of look at these, keep in mind that this is a review. So we're not going to get into the details of defining atomic radius. We've done that already. We're going to kind of get into what's going on and what the trends are and why they're happening. So as we kind of look at notice our flow chart, we'll kind of work our way through it. But as we kind of look at what's happening and kind of look in what's going on between the nucleus and the electrons. So, there is an attraction between the nucleus and the electrons that are around it. That attraction keeps the electrons from flying away and flying out from the atom. And there are a couple of factors that play into how much attraction there is from between that nucleus and those electrons that are around it. So one of the things is the size of the nucleus. More protons, more positive charge, more attractive force between the nucleus and the electrons. The other factor is how far the electron is from the nucleus. The closer the electron is to the nucleus, the more it is going to feel the attractive force of that nucleus and the more strongly held it's going to be. The further away from the nucleus, the further away it is from that attractive force, and the less it's going to feel that the attraction of that nucleus. And so remember, the electrons that are furthest from the nucleus, outermost electrons, furthest away, those are our valence electrons. Those valence electrons, remember, are the ones that also are gained or lost when atoms form ions. So if this is our electron of interest, there are a couple of factors that are going to affect how strongly it is attached and attracted to the nucleus. There is the net attraction between the nucleus and that electron, and that net attraction is what we call the effective nuclear charge. The effective nuclear charge, and there is a quantitative way of calculating it, we're not going to worry about it, but it is a measure of what is the net positive attraction or positive pull that a particular electron is going to feel for the nucleus. The closer the electron is to the nucleus, the higher that effective nuclear charge is, the more it's going to feel the attraction of the nucleus. The larger the nucleus, the more protons, the more attractive force that electron can feel from the nucleus. Okay. And so one of the things that can reduce the amount of attractive force that an electron feels is how far away it is, how many other electrons are between it and the nucleus. So electrons that are further away are going to not only be further away from the nucleus, but there's going to be more electrons between them and the nucleus, blocking some of that pull that the nucleus has and shielding our electron from feeling the complete attractive force of that nucleus. So that shielding effect can also reduce the positive pull that an electron feels. And so what happens between what we're going to talk about when we talk about groups and periods, it's really how that attractive force is changing as we go across the period and as we go down a group. So we're going to start with the group trends first. So we're going to kind of zoom out here so we can get back to our table. And we'll go with our group trends first. And so when we talk about our group trends, going down a group, there are a couple of changes happening within the nucleus. Right? So as you go down the group, right, we are adding more energy levels, right? We're adding more layers to the atom. So we're adding more electrons, we're adding more layers, we're adding more electrons that are further away. And as we are making a bigger nucleus. So we are making a nucleus that has more positive charges, and so should also have a stronger attractive force. But as we go down that group, even though the nucleus is getting larger, those electrons that we're adding are further and further away. And it's that increased distance from the nucleus that has a greater effect on things than the nucleus being larger. So the fact that those electrons are further away means that even though the nucleus is getting bigger, the distance that they are from the nucleus wins out. And because they're further away and there are just more electrons between those new valence electrons and the nucleus, right, the pull and the attraction that those new electrons that are at the outer rim, those valence electrons that they feel from the nucleus, diminishes. And so what we see is as we move down a group, those electrons that we're adding are further and further away and have an increasingly diminished attraction to the nucleus. So they're more weakly attracted to the nucleus, and therefore they're not held on as strongly. And so as we look at some of our periodic trends, we're going to come back to that idea, and we're going to start off with just the size of the atom. And so as we look at atomic radius, right? So that's just what it sounds like. It's the radius of the atom. You can go back and look at the definition and how they measure it, but it isn't just, in other words, just a measure of the size of the atom. And as we go down a group, remember in our main group elements, which is groups 1 and 2 and 13 to 18, this is using an older numbering system that you see with Roman numerals and A's. Right, so notice there's no transition metals, but we see going down a group, there is a general increase in the size of the atom. And again, it goes back to how well that electron, that is those outer electrons, those valence electrons, goes back to how well they are being held and how attracted they are to the nucleus. Right? Their increased distance means that, again, they're further away, and even though the nucleus is getting bigger because there's more protons, the fact that those new electrons are further away wins out. And it's that increased distance that really diminishes the attraction that they feel for the nucleus. And so the atoms get bigger. And we see that going down a group. There's a very, very steady increase in the atomic radius. And one of the other factors that is affected by this is if those outer electrons are further away and they are feeling the attraction to that nucleus much less, that means they're not held on as tightly to the atom and they're easier to lose. And so that's where we see kind of, when we look at some trends in another periodic trend called ionization energy, which is an energy. It's an energy, it measures the energy that it takes to remove the outermost electron. Well, if we look at those group trends in ionization energy, we see that the amount of energy it takes to remove the very last electron decreases as you go down the group. So as the electrons get further from the nucleus, and as their attraction and hold that they feel from the nucleus decreases, it becomes easier for them to be removed, and the ionization energy decreases. And we see that going down our main group elements. So again, even though the nucleus is getting larger because there's more protons, the fact that those valence electrons, those outermost electrons, those electrons being added, are further and further away wins out, and the nucleus just can't hold on to those electrons as well because they're further away. There's more electrons blocking them from the nucleus. And so, the attraction that the nucleus has for those outermost electrons really does diminish quite a bit, and they become easier to remove. When we talk about other periodic trends, one of the results of having those electrons that are easier to remove is that as we go down a group, we see that there's an increase in metallic properties. And so, metals have a lot of properties that we've talked about, but one of them is that they form cations, they form positive ions. They readily lose their electrons when they form ions. And it's because, as we go down those groups, and those valence electrons are easier to remove, well, electrons that are easier to remove means that you're going to have elements that form cations. And so you're going to have elements whose metal properties are more pronounced at the bottom of the group than at the top of the group. And so we'll come back to that, losing electrons, and how it relates to properties as we talk about in a few minutes about some of those properties of kind of specific alkali metals and specific groups. Now, as we talk about losing electrons and forming ions, we can't ignore the size of an ion or ionic radius. Now, you'll notice that in general, ionic radius and atomic radius follow the same trend for the same reason. But there are some important things to point out. First of all, if we look at, for the metals, if we look at the size of the neutral atom in gray and the size of the ion, you'll notice that when that metal loses that valence electron, when it loses that electron to make an ion, its size decreases. So that for cations, the cation size is always smaller than the neutral atom. Because think about it, the nucleus is not changing. You have the same size nucleus, but now there are fewer electrons to hold on to. So all the electrons feel a greater positive, greater pull from the nucleus, and that nucleus just kind of pulls everything in that much tighter. Okay. As we go to the nonmetals, you'll see that the nonmetals form anions. It's the opposite behavior. The nonmetals have a very strong attraction to electrons, and so they will fill and they will form anions. And so notice that for our group, our nonmetals, that the neutral atom in gray in this case is smaller than the anion. Right? Again, for our similar reasons, the nucleus is not changing, but now that nucleus has more electrons to hold on to. And so that means that the attraction that those new electrons are going to feel for the nucleus is going to be diminished, and they're not going to be held on as tightly. And so the ion becomes larger than the neutral atom. Okay. Notice that for ionic radius, you do see the same trend as atomic radius going down the group. The ions do get larger. When you're comparing these, you do have to be careful that you're comparing apples to apples and oranges to oranges, so that you're comparing cations to cations and anions to anions, because you will see a break in the periodic table And so you really have to kind of be careful that you're not trying to compare the size of a cation to the size of an anion, because it becomes difficult unless you know they're very far away. Okay. Right. So some other things. Electronegativity we've talked about. Electronegativity, remember, is the only periodic trend that relates to how well elements are attracted to electrons in a chemical bond. And so remember, it goes from a scale of 0 to 4. It is a unitless value, 4 being the highest. So and it's that electronegativity difference that we use to tell the type of bond that is going to form. The bigger the electronegativity difference, the more likely you are to have an ionic bond. And so again, it becomes kind of a measure of how strong that nucleus is. Notice that the elements with the highest electronegativity are the ones that are nonmetals. The elements that have, generally speaking, that have fewer electrons in relative, but whose nuclei are large in comparison to the number of electrons that they have. And so again, as we move down the group, notice that the ability of the atoms to attract electrons in a bond becomes less. The electronegativity becomes lower, because now, again, even though the nucleus is bigger, there are so many electrons that the nucleus has to hold on to, and they're so far out that those atoms don't have the attraction that those nuclei have for those very outer electrons is very weak. And when it comes to attracting the electrons of other atoms, well, that's even more difficult, because now you're talking about not only is the attraction of the nucleus to the valence electrons of its own valence electrons diminished, because those valence electrons are so far out, but now you're expecting it to pull and attract other electrons. Right? It can be very difficult for that to happen. And so we see that electronegativity decreasing going down the group. Right? Now, a couple of other things we'll see. If we look at the reactivity in a group, we'll see that there's some trends in reactivity. That as we talk about the alkaline metals, we'll see that the reactivity of those alkaline metals is going to be affected by what is happening. And so I am going to put in these videos, I will post them separately, but I'll post a separate link with a separate discussion just talking about these videos and the reactivity. Okay? So no, we'll come back to these. If we kind of zoom out in our flowchart and we kind of look at the period trends, again, notice same thing, right? We have electronegativity, ionic radius, metallic, atomic radius, ionization energy. If we kind of start with atomic radius, you'll notice that as we move across the period, that the atomic radius in general decreases. Why? Well, as we move across the period, are we changing anything in relation to is the nucleus getting larger? Yes, right? Because we're increasing proton as we move across the period. However, the important thing, one of the important things that really affects the properties we see of the elements is that the nucleus is getting larger, and we are adding electrons to keep the atom neutral, but those electrons are not being added further away from the nucleus. They're being added to, if we want to think of the atom as stadium seating, they're being added to rows of stadium seats that are already there. And so we're not adding additional rows further from the nucleus. So we're just kind of packing electrons in to spaces that are already available. And so what that means is that as we move across the period, the nucleus gets larger and there are more protons. And even though there are more electrons, those electrons are not further away from the nucleus. And so what that means is that the effective nuclear charge, that net positive attraction that the electrons feel from the nucleus, actually increases across the period, even though we're adding electrons. Because those electrons are not further away, and so they're not more shielded, and so the nucleus gets larger, and that kind of wins out over the number of electrons, and we see an increased attraction of the electrons to the nucleus as we move across that period, which means that because the nucleus has that greater positive charge and all of the electrons are in general feeling more of that positive charge, they're all held on much more tightly to the atom and the size decreases. That also means it's going to be harder to remove those electrons. And so we see that in the ionization energy, because as we go across the period, we see that there is this increase in ionization energy. It becomes more difficult across the period to remove those electrons because we see that the nucleus becomes larger, and the effective nuclear charge, the net positive charge that all the electrons are feeling for the nucleus is increasing, so they're held more and bound more tightly to the atom, so it takes more energy to remove. We do see some blips where in the ionization energy where there are more stable arrangements of electrons, and those more stable arrangements lead to it being more difficult to remove those outer electrons. But we do see that you'll see that in group 2, you see that in group 15 and group 18. Right? And so these just represent more stable electron arrangements, that's all. As we talk about ionic radius, again, going across the period, we see that the trend in ionic radius mirrors or parallels the atomic radius trend. But again, if we look at the ionic radius, we do have to compare same to same, cations to cations, anions to anions, but there is a general decrease when we're comparing the same thing going across the period, and we see that group trend as well. Electronegativity, again, as we move across the period, and we see that the nucleus becomes has an increasing effective nuclear charge, and so that net positive charge that all the electrons are feeling increases, and so everything is held more tightly. We see that the electronegativity increases, meaning that these elements with very high electronegativities have very highly positively charged nuclei for their size. And so something like fluorine, only has 9 protons, given its number of electrons, its nucleus is small but powerful. And so it has a very it has a very high electronegativity because it has enough protons to not only hold on to all of its electrons very tightly, but it's a good balance between size and nucleus size and atom size, where the nucleus is positively charged enough that it can hold on to its electrons really well, but it makes for a small enough atom that it also is able to attract electrons from other atoms really well. And so we see, again, notice nonmetals, right, that tend to be closer to the top of the groups, that tend to have nuclei that, in relation to the atom size and number of electrons, exhibit a higher effective nuclear charge, tend to have higher electronegativities as well. When we talk about metallic properties, again, right, when we talk about those group properties, we see that the ability for atoms to lose electrons means that those very outer valence electrons seem to be less tightly bound to the nucleus. And so as we move across the period and the overall effective nuclear charge kind of increases in relation to the number of electrons and the size of the atom, we see that we go from elements having metals to elements having nonmetals. Again, and so we see those metals being kind of to the left, where it is much easier for the atoms to lose those valence electrons because the effective nuclear charge that is experienced by those very outer electrons, the attraction they feel for the nucleus is less on the left side of the periodic table. So that is as brief an overview we can do of periodic trends. We will see a second video posting where we'll talk about reactivity in the groups that you can watch separately as we're reviewing, just so this video doesn't get too long. Good luck, and have a good week.